welcome to this class. So now let us move on to one other interesting idea called GAN inversion. Before we get there, I will talk about, I should have talked about the latent variable models and then get to this. Anyway, let me just roughly introduce. See, what is a GAN doing? It is taking an arbitrary random variable, okay, projecting it onto the ambient space. Okay, before I forget, I should tell you one important thing. So typically this is how it would be. This would be Rk and this would be Rd, and k is much less than d. Somebody asked me in the first class that why is this k less than Rd, less than d. It is because of the manifold hypothesis. So when you train a GAN, I have been writing the generator in this way, right, where the input dimension is much lesser compared to the ambient dimension. It is because of the manifold hypothesis that we believe that the data can be supported well using much lesser dimensions compared to the ambient dimension. In fact, as I told you, we have some in some of our previous work we have solved, we have actually asked the question of does there exist an optimal k such that you get the best performance, and it turns out that there exists an optimal k. Anyway, so point is that typically what happens is all these samplers starts from a lower dimensional space and then projects it onto the ambient space, and because the manifold hypothesis is believed to be true that you can always start with a lower dimensions and then project, that is the idea. Okay. This is what a GAN is doing, right. So this is a sampler, so this is sampler. Some applications in machine learning demand that we do the other way around also, which is that we take data in the ambient dimension and project it onto another space which is of lower dimensions. So this is Rd and this is Rk. We already know ways to do this. In classical machine learning, do you know how to do this? So component analysis is one way to do this, right. It is also called the dimensionality reduction, where you start from ambient space, and this is a linear way of doing it. Now we will see later in the course that the methods that we will look at, things like variational autoencoder and so on, they actually do both, which is take the data and project it onto a lower dimensional subspace, and from the lower dimensional subspace you get back to the data ambient space, and this transformation from the lower dimensional space to the data space are samplers. And the other way around, what are they called? They are called, this thing can be embedding extraction, embedding or feature extraction. By the way, this course is the offline version of this course is named as representation learning, right. This is representation. So data, the projection of data onto a lower dimensional space is what is called as representation or embedding. So we have all kinds of embeddings today, right. If you take textual data, you have, it is not the raw text or the ASCII characters that gets fed, it is an embedding that gets fed to these neural networks. What is an embedding? Start from the raw data space and project it onto a lower dimensional representation space, that is what is called as an embedding, okay, or representation for that matter. I have named that lab also as a representation learning lab, okay, because compressing data onto, see, the entire idea of intelligence, a little bit of philosophy, is that when would intelligence emerge? One theory is that if you compress information, compression of information is what intelligence is all about, isn't it? See, the amount of data that human beings have produced over time is humongous. All that is getting compressed in a mere trillion numbers, isn't it? Even though trillion is a big number, compared to the amount of data that human beings have produced, it is a small number. So it is because of the fact that we are able to compress so much information into a billion parameters, a few billion parameters, that the intelligence has emerged. So compression of information is what knowledge is one way to look at it. Anyway, so this is representation learning, right. You have projection from the data space to the, typically this is referred to as the embedding space or latent space, okay, or representation space and so on. So, I will be using those words interchangeably. Now, this sampler that we saw so far using this paradigm, right, can handle projection from the latent space to the data space, which is a sampler. What if we need the other way around also? Why do we need this, by the way? Can somebody think of an application where we would need the other way around also? Why do we need an embedding? Let us say that we are looking at images. Why do you think representing every image, what do you mean by embedding again? Every data point, if that can be represented using some vector which has in a space endowed with good distance metric, that is called representation. Why do you, can you think of applications where you would need vector embeddings for data? Yeah, some semantic clustering is one reason why one would need that. Suppose you have a large amount of data and you want to find out categories in it. So, in an unsupervised way, that is one way to do it, one application. So, the other applications that one can think of is let us say that you need to do an image based retrieval or image based search. So, you are running an e-commerce website and somebody uploads an image and you want to find whether that a similar thing of similar product exists in your catalog. How do you do that? So, convert all those images into vectors and do a vector search, vector DB search over those vectors, and then you retrieve. So, that is one application. The other interesting application is image editing. So, let us say that, I mean, you might have seen all these use cases, right, where you have uploaded your picture and you want that picture to be modified into some other style. Let us say that the spectacles have to be put on or whatever, right, all these kinds of things. To do that, what you have to do is first, given a particular image, you need to find the corresponding embedding of that image, okay, and do a traversal in that embedding space while generating. So, what people found out is that once you, if you train a GAN, there exists particular directions in the latent space which corresponds to semantic variations, which is, let us say that you take some z1 as the embedding corresponding to an image x1, write it here. So, x1 has an embedding z1, okay. Now, you take z1 and maybe take some z2. So, x2 has an embedding z2. You take two images, okay, and get the corresponding embeddings. How do we do this transformation in with the GANs framework? I have not told you that yet. I will talk about it. But let us say that there is some way to get the corresponding embedding. If I do a linear convex combination of that, linear combination of those two embeddings of two images, I would, what people have shown is that this direction from z1 to z2 corresponds to the semantic variations between the image of x1 and x2. This is the latent space traversal. This is how you, let us say that this is an image of a person and this is the image of a person with a spectacle or something, right. If you make that traversal between the latent vectors of those two images, it will convert this person to this person. So, that is what is going to happen. So, basically there exists semantically meaningful directions in the latent space, okay, which when traversed will impose a particular type of style or semantic information on the other image. So, if you have to do all these applications, there should be a way to know what image, what vector in the latent space corresponded to this particular image, right. But the GAN that we have constructed so far does not have that capability. It cannot ingest an image as an input. It can only take a vector from the normal distribution or any the latent space and convert it into a data space. It cannot do the other way around. So, now the question is, one is interested in inversion of the above function, right, that is, given an image from Px, find the corresponding z such that if you pass that particular z to the sampler, it will give you xi that you started from. You have a fixed image. I need to find what point in the normal distribution would have generated this image under my GAN. So, can I get that? Okay. These techniques are called inversion techniques. So, if you have a sampler, you should also have an inverter. I mean, because that's when the story is complete. Have you heard of these terminologies? People talk of encoder decoder models, encoder only models, decoder only models, and so on. This process of projection from data space to the latent space is called encoding. This is encoding. Okay, this is called decoding for obvious reasons, right? Take the data space and compress. This is called encoder decoder. So GAN is a decoder only model, and all the language models that you see, the transformer based autoregressive ones, are all decoder only models right today. Okay, they cannot give you embeddings, they cannot give you the representations, they can only sample. Okay, an encoder decoder model would have both the directions, where you can project, handle both the directions, uh, and yeah, so an encoder only model, so PCA for instance is an encoder only model, because it will only give you one direction of projection from data to the latent space, not the other way around. Okay, so that's the terminology, the encoder decoder model and so on. Okay, anyway, so now the question is that how do we, yeah, already talked about it, feature extraction, data manipulation, editing, etc. Now the question is, how do you modify the adversarial framework such that the inversion is possible? Okay, in fact there is a nice anecdote on this. This thing can be done using what is called as bidirectional GAN, okay, or also known as Bi-GAN. This exact same approach, okay, is proposed in two different papers which appeared in the same conference in the same year. They were concurrent submissions. One is called adversarially learned inference, ALI, the other is called Bi-GAN. Both of them are exactly the same idea which appeared in the exact same conference. They are concurrent works. So this kind of thing can happen. Okay, if you are working on something, I was reading so there was a meme somewhere that was going on. Let me recollect that. Researchers, academic researchers, realizing that the problem that you are trying to solve is being solved by multiple people, is being considered by multiple people in the world, and it is solved in a better way than you by others. So that's the process of research. is what I read. So always this happens, right? I mean, you're not the only person that is working on that particular area, and people would solve it. Yeah, so this is called bidirectional GAN or adversarially learned inference. Those are the two papers that you should be looking at. So what's the idea in the naive adversarial learning? You have the sampler network that would take Z and project onto X, and you have the critique function that's a classifier from X, that's a classifier on the distribution upon which X is supported. So in bidirectional GAN, no, in addition to the sampler and the critique network, there is another function called the encoder or the inverter, which is approximated using a neural network. So there are three neural networks here. One is the sampler or the so called decoder, which is a projector from Z to X, and you have an encoder network that would take X as an input and gives you a sample from the latent space, and you have the critique network, of course, that would construct the bound. What is the objective? In the bidirectional GAN, right, the discriminator is designed to classify between the data tuples of the form x comma e phi x and g theta of x comma z. What do you mean by this? See, okay, so before we go, I'll tell you what distributions are. So now the input to the generator is from the normal distribution, let us assume, okay, and it will give you the samples from distribution p theta. So input to the encoder are points from px, okay, and it will give you some z. You will have to ensure that the dimensionality of this matches with this, of course, okay, that goes without saying. So let us say that it gives you z cap, okay, which has some distribution p phi of z cap. What is our goal? Our goal is to, okay, so let me get to our goal in a while. So this is p phi of z cap, and the discriminator, of course, is a classifier between them. So what is done in bidirectional GAN is that you make your classifier classify between tuples. What sort of tuples? It takes a generated g theta and the corresponding z, which is an input to the sampler, that is one pair. The other pair is the true data x, okay, and the output of the encoder. What do we need now? We need the joint distribution between x cap and z to match the joint distribution between x and z cap, is not it? That is when we have both the sides done, right. So, x z, we have x that is giving me some distribution z cap. I need the joint distribution between these two to match the joint distribution between x cap and z. If this happens, all the marginals match. So, the only thing that you should do is that you make sure that the discriminator, instead of classifying between samples of px and p theta, it would now classify between the tuples of these two distributions. All that I am doing is treating z as some additional dimensions of the data that I am trying to generate, that is it. So, now what happens? This is the objective. Now, we have the same optimization problem, okay, but the minimization now is over both theta and phi, where phi is the encoder network, which takes x and gives you z cap, and the classification now is between the tuples of it. So, the discriminator will take x comma e phi and g theta comma z. So, instead of the previously, right, this was x, this was x cap. Now, this is x comma z cap, this is x cap comma z, that is it. Okay. Now, once this bidirectional GAN is trained, so remember our objective is to ensure that we have both the sampler and the embedding extractor or the encoder. So, it is very easy, right, treat the generator network for sampling and the encoder network for inversion. If you are given an image, pass it through the encoder network to get the embedding corresponding to the image. So, if you take that same embedding and put it through the sampler, it should give you the image that you started with. In fact, yeah, this is a result that you can show, again do the algebra. What can be shown is the optima of this optimization problem is achieved if the joint distributions match, and these joint distributions are such that the marginals correspond to the individual distributions. So, this can be shown, and please do it. That is why I am telling you that you have to go and read the papers, and most of your exams will depend on these kinds of, the ones that have left as algebra you have, I assume that all of you have done that, okay, when I am setting the question papers. Okay, so I think I will skip this. Okay, so before we close, there is one other piece that I would want to cover, and then we will close. See, one question, as I said, is okay, you have constructed a generative model. How do we evaluate its goodness? How do we know how good is the generated, how good are the generated samples? Multiple metrics exist. Again, this is one widely used metric, and because we are looking at versus trends metric, etc., I will talk about it. There is a widely used metric, okay, which is called FID. This is called the Frechet inception distance. It stands for Frechet's inception distance, FID, which is one of the standard measures that is used to calculate the goodness of the generated data. Okay, I will explain what this is, and then I will run through the writings. Let us say that you are given n number of samples from the true data and n number of samples from the generated distribution. This is post training, you have trained and you have n number. So, what we have to compare is that how close or far these are. Again, we have to look at a sample estimate, we do not have distribution level measures. What is a good distributional measure is, see, one high level idea is we can compute the exact same metrics that we used for optimization on these samplers, that is it. So, you can compute Wasserstein's 2 metric for instance, if you compute Wasserstein's 2 metric between the post training generated samples and the true samples, that would give you a good measure of how close or far these two distributions are, correct. That is what FID is doing. Frechet's inception distance is the Wasserstein's 2 distance between the actual samples and the generated samples, but with a twist. It is not exactly between the images of the actual images and the generated images, but there is a bit of twist that is there, which I will talk about. But at the outset, it is simply the Wasserstein's 2 distance between the true data and the generated data. Okay. How do they compute the Wasserstein's metric? We can't, as we saw, no, it is very hard to solve that optimization problem and all that. How do we compute Wasserstein's 2 metric? This is how it is done. First, they take the images from the true and the generated data and extract the embeddings of those images on a pre-trained neural network. The neural network that is pre-trained for some other task. In this particular case, they use what is called as Inception network. So, this Inception network is a large neural network, an architecture that is trained on the ImageNet. ImageNet is a data set. You train the Inception network on in an unsupervised way on the ImageNet task. Pass all the images that you have, both the true and the generated data through that Inception network, and extract embeddings from a particular layer of it. And people have found out that perceptually there exists some layer, I do not recall what the exact number is, some 68th layer or something in the Inception network that corresponds to human vision somehow. So, they extract the embeddings from that layer of the pre-trained Inception network. Now, what is happening? All the images are now converted into a vector of the dimensions equal to the dimension of that Inception network. You understand? Okay. Now, they assume that the distribution that this latent space of that Inception network is following is Gaussian. Is that a good assumption to make? Suppose you have used measures like batch normalization and some kind of normalization layers in your Inception network, it is a fair assumption to make. Right? If you have enough number of samples, you can invoke things like central limit theorem and say that it is fairly Gaussian, but at least procedure wise this is what is done. You assume those to be Gaussian. So, now what you have is, you have samples from 2 Gaussian distributions, one that corresponds to the true data, one that corresponds to the generated data. Are you seeing what is happening? Take the images from both the generated and the true distributions, pass it through the Inception network and tap the embeddings from a particular layer. Assume both of them to be coming from Gaussian distributions. Now, what you have is samples from 2 high dimensional Gaussian distributions, compute Wasserstein's 2 distance between them. Now, Wasserstein's 2 distance between 2 Gaussian distributions has a known algebraic form which is given by this. You take the mean of those 2 distributions, compute this, and you compute the trace of this particular quantity, the variance of the covariance of the true data plus the covariance of the generated data minus this particular thing. Wasserstein's 2 distance between a pair of high dimensional Gaussian distributions has a deterministic form. We have everything that we need, right? We have the mean of the true data, we have the mean of the generated data, and of course the variance of both of it, because we have those vectors. Compute this. This is what is called as the FID. This is called Frechet's inception distance. So, if you are given so if you are given data from the some samples from the true data and the generated data, take a pre-trained Inception network, okay, trained on some data set ImageNet, pass both the true data and generated data through the above Inception network, tap the embeddings at some nth layer, okay, and extract features for both of it. What you have is the corresponding vectors now. Assume both of them to be Gaussian, compute the mean and the covariance of it, and then compute the Wasserstein's 2 metric, that is the Frechet's inception distance. It is called inception distance because you are using Inception network to tap it. And what people have found out is that the lower the FID is, better the perception, better the quality of generated data is, because it corresponds to Wasserstein's 2 distance. Of course, there are flaws here, right? I mean, why should they be Gaussian distributions, and why should you use an Inception network, and what layer to tap, and so on. That is why people have come up with other metrics also, like Inception score and so on. But anyway, so where they give up the Gaussianity assumption on the distribution and so on. But FID, this is how it will give you a broad idea of how it is done, right. Take some embedding, assume a distribution, and compute the distance metric between them is how to do it. Okay. Right. So that brings us to the end of the F divergence minimization on adversarial learning. There are multiple applications of adversarial learning. So even though adversarial networks are not the min-max optimization problem is not the state of the art today for image generation, they are diffusion models. Adversarial learning is used in multiple places. So for instance, when you build these, I do not know how much of this will make sense. When we build autonomous agents for different tasks, you have multiple LLMs that are building agents. So typically we construct what are called as adversarial agents, self-correcting adversarial agents, where you have an LLM that is proposing a hypothesis, and you have another LLM which is trying to negate that hypothesis as a critique. And we solve optimization problem on the prompt space, or do a parameter efficient fine tuning, which we will see later in the course, PEFT, okay, which is training a few small set of parameters on these agents so that the performance gets better. So this whole idea of having a critique network that would critique the performance, and there is the sampler network, and there is an adversarial optimization set between those two, is a nice idea that gets carried to multiple state of the art models as well. Okay, true in life too, right. So you, if you have to generate good data, you should always have a good critique. Even in control systems we have this idea, the system gets stabilized only if you have negative feedback, isn't it? Do you remember, I do not know if any one of you studied the electrical engineering, we have that operational amplifier where you have the negative feedback. I do not know, if you study computer science you do not understand this, right, undergrad. So electrical engineers have this advantage. In fact, we study something called state space models later in this course. They have their roots in what is called as the linear dynamical systems, the Kalman filters that we studied, that we study in control systems, right, in our undergrad days. Anyway, so I have slight bias towards electrical engineering because because a lot of those ideas cross pollinate. Anyway, so point is, this idea of having an adversarial or a critique network is a handy idea, and you can use it for multiple applications. Okay, so that is it for adversarial learning. Next we will move on to another class of models called latent variable models, which by construction has both encoders and decoders baked into it. And we look at multiple models in this family. One is the variational autoencoder, the other is the diffusion models, then we look at some of the autoregressive based models and so on. That's how we move on in the course. That's it for today. We'll see you in the next class. Thank you.